Okay, good morning everyone. We're still waiting for a few more people. I don't know if they're going to show or not, but we're going to get started. We had a little bit of a break yesterday. I just felt that moving on to the next lesson might have been a little bit rushed. Good morning, Shezmaida. So we ended it after the first lesson. Good morning, Farhan. The only thing we learned yesterday was about mass and weight. Well, there's a lot of things we learned concerning mass and weight. You are expected to know the conceptual differences and definitions of mass compared to weight. Mass is a measurement of a quantity of matter. It's how much stuff an object is made of, and it's measured in kilograms. And assuming that it's the same object that moves from place to place, either on Earth or throughout our universe, the mass is determined by the properties of the object, and the mass is what the mass is. It doesn't change. The weight, however, should always be thought of as the force due to gravity. And the force due to gravity, we will learn later on more about gravitational forces, but a force of gravity acting on a mass depends basically on two things. It depends on the mass. So a more massive object has a greater force of gravity acting on it. And it also depends on the gravitational field strength. And the gravitational field strength can also be thought of as the acceleration due to gravity, but I prefer to call it gravitational field strength. We had a little bit of a discussion. I think Andrea yesterday had asked about, I think she asked, does the weight depend on the location in space? Is it dependent on the location in space? And the answer is yes, because different locations in space have different gravitational field strengths. So the gravitational field strength on the moon is different than the gravitational field strength in Wetaskiwin. And that's different than the gravitational field strength in Calgary. I've mentioned this before in class. I don't think I mentioned it when we were online. If you start talking about the local value of the gravitational field strength in Wetaskiwin, the gravitational field strength is 9.81 meters per second squared, and it's down, so it's negative. If you look at the gravitational field strength in Calgary, it's negative 9.80 times 10, not times 10, meters per second squared. And the reason for that is Calgary is at a slightly higher elevation than Wetaskiwin is. And what that means is when you look at the mass of the Earth, which causes gravity, if you're standing in Calgary, you're a little bit further away from the Earth because you're higher up compared to standing in Wetaskiwin. So this gravitational field strength, you can look online and there's a map, an interactive map by a government agency in the States called the Geological Survey Organization, and it shows gravitational field strength at any place on the surface of the Earth. It's kind of an interesting thing to look at. Anyway, this is the formula that we learned relating weight, mass, and gravitational field strength, and you had a few questions to do concerning this formula. Some of these questions turn into kinematics questions where you have to use the gravitational field strength as the acceleration due to gravity for moons or planets or other places. Can you please take a look over your work and see if anybody has any questions you would like me to go over from this lesson? All right, seeing none, we're going to move on. And we're covering two lessons today. This actually works out pretty good by postponing yesterday's second lesson to today, because both of the lessons we deal with today are concerned with forces of friction. So this section is And the numbers here are wrong. This should be 20.2.6. And the title, I keep forgetting to change the titles. The title, I believe, is Normal and Frictional Forces. Is that correct? Okay, thank you. So we're looking at normal and frictional forces, section 20.2.6 in your note package. And we're going to talk about what a normal force is first. A normal force is a type of force. It's not, the word normal here doesn't mean what it would mean in English. I don't mean this is a regular force or this is a run-of-the-mill force. What I mean is it's a force that acts normal to a surface. And I'll talk about what that means in a second. But basically, whenever you have an object with mass on a surface, assuming gravity is around, there's going to be a force between that object and what it's resting on. I've talked about this before. I'll give you a different example. If I were to put a book down on a table, what's going to happen is the book is going to be pulled down against the table, but the table is going to push up against the book as well. It's a little bit of a subtle idea, but what it really is Newton's third law of motion. If I rest all of my body weight on a table, but there's a set of keys between the table and my hand, then I will be exerting a force downward on the keys. And I think I've mentioned this before. When I lift my hand up and look at the palm of my hand, the palm of my hand will have an indentation of the keys on it, which means that even though I was pushing on the keys were pushing back. So that force is called a normal force. We abbreviate it with F sub n. So this is what we always use for normal force. Now you want to be careful because we also have some notation for F net. And I want to be abundantly clear here that F net is not the same thing as Fn. If we want to say net, we write the word net. We don't abbreviate net by putting n because we could confuse that with a normal force. And the key idea here is that the normal force acts perpendicular to the surface. In fact, the word normal in mathematics means perpendicular. Okay. So we've got a question to start thinking about these forces with this question. It says, consider a mass resting on a horizontal surface. Explain why the normal force is equal in magnitude to the force due to gravity. So we've just got this box, whatever it is, a block of wood, a piece of metal, it doesn't matter, a desk, it's sitting on a surface. If we were to draw a free body diagram, I want to remind you what a free body diagram is because it's going to play an integral role in all of our force analyses in the rest of this unit. A free body diagram shows all forces acting on an object. So the object in question here is this box. What are the forces acting on it? Well, we know that there is a force of gravity acting on it because we're talking about on Earth here. I don't have to say in every single question, oh, by the way, we're talking about on Earth. So there is a force due to gravity, which of course we abbreviate with F sub g, and we put a vector symbol there because direction is important. Now, if you start to talk about Newton's first and second laws kind of rolled into one idea, Newton's first law says that if an object has a particular velocity, and this object does have a velocity, the velocity of this object is 0. Newton's first law says if an object has a particular velocity, it will keep that velocity unless there's an unbalanced force. And then Newton's second law is a way to calculate how the velocity changes in terms of acceleration. So when you look at this, and I'm going to erase this big bubble in a second, but when you look at this, if that is a free body diagram, then the only force acting on the object is the force of gravity, and that means we have an unbalanced net force. This box would accelerate. But it doesn't accelerate. And kind of putting this together with Newton's first and second law, since it doesn't accelerate, the forces have to be balanced, which means that the net force acting on this object must be zero. And the reason for that is that the acceleration is zero. So all of these ideas go together. The net force is zero. Why is the net force zero? The net force is zero because the velocity is constant and unchanging, which means that the acceleration is zero. I'm talking here, and I could just cut to the chase, but I think there's some subtler ideas here, some slippery ideas that we need to really think about. I'm talking about uniform motion. Let that sink in for a second. What we are dealing with here is uniform motion. Now, the word motion typically conjures up movement, but uniform motion means constant velocity, and 0 meters per second is constant. That's really subtle. This is uniform motion even though the object isn't moving. It's uniform motion because, at the risk of being repetitive, it's uniform motion because the acceleration is zero. And the acceleration is zero because the net force is zero. Okay, time to get back to the question. If the net force is zero, then there must be an opposite force acting on the object, and that opposite force must be exactly equal in magnitude to the gravitational force. And that force is called the normal force. That normal force, and I don't want to muddy up this diagram too much, but I told you that normal forces act perpendicular. It's perpendicular to the surface because this force is perpendicular to the surface. That's why it's called a normal force. Now, the question was explain why the normal force is equal in magnitude to the force due to gravity, but before I do that, I have a question for you. In this situation, I'll go to a new page. In this situation, I want everybody to think about whether what I've just written is a true statement. Is this true? And this, although it may seem very unimportant because you can probably still get correct answers, this is a vitally important idea, particularly next year, but also moving on this year. This is false. The net force is not equal to the normal force. The net force is equal to zero. Okay, so that's the first thing to note, that F net, so this is false. F net I'm not sure why it's doing that. Give me 1 second to find out what's the deal here. Oh, that's interesting. Okay, the net force is equal to zero. That's what the net force is. I have a different question for you, and then we'll finally finish off this question in your notes. True or false? Is this a true or a false statement? And I would be willing to bet that the vast majority of you, and I'm not going to put you on the spot and ask you to type responses, but the vast majority of you will say that that is a true statement, and you would be wrong. This is not a true statement. And I'm not trying to mess with your head here. I'm not trying to intentionally confuse you. This is false. Oh, that's really interesting. Okay. I got to stop doing that then. This is false. I will ask for somebody to maybe volunteer, and you can type a response if you want. Why is it that that's false? Perfect. Taylor said different directions. Force is a vector which has direction. And when we take a look at the diagram, the normal force is towards the sky and the gravitational force is downwards. And Andrea explained it in a different way. Yes, it is because the normal force is perpendicularly up and the gravitational force is down. So we cannot say that these two forces are equal. What we can say, and again, this is really subtle, is that these two forces are equal in magnitude. So we don't say that we don't say that Fn equals Fg. What we say is that because there's zero acceleration, we write this. F normal magnitude equals Fg magnitude. This is a true statement. But you need the absolute value symbols there, because if we don't have them, you're saying they're equal in magnitude and direction. So what have we learned here? We've learned that if you ever, this is why we're doing this, if you ever need to know the normal force for an object on a horizontal surface, which it will be for the first lesson today, if you ever need to know the normal force, what you can do is calculate the gravitational force instead, because that number will be equal in magnitude to the normal force. There is no way for you to directly calculate a normal force, but you can calculate the gravitational force in its place because they're equal in magnitude. Okay. Now, what are frictional forces? We have some kind of idea about frictional forces. If you're pushing a car because it's stalled, I'm not talking about it being stuck in snow, but you're pushing a car and it's stalled, and the person has put it in neutral, and it's raining out, so there's water on the car. If you put your hands on the water with kind of plasticky gloves on, you'll find that your hands slip quite easily and you're not able to apply much force. That's because there's a lot of friction. The reason why you can skate on a skating rink is because there's very little friction. The reason why I can walk up a very steep hill without hurting myself is because there's a lot of friction. Now, when two objects are in contact with one another, there is this force of friction, and it will always oppose the motion. This is one of the most important things about friction. Friction is this mysterious force that always acts backwards to the direction that you are trying to move an object. So if I have, what's an example? I bought an old deep freeze that I took off of my truck the other day to put in my garage. If I were to take that deep freeze and push it towards the north in my garage, I feel this opposing force towards the south. But if I were to push the deep freeze towards the south, I feel this opposing force towards the north. So it's always opposite. Now, usually, this isn't always the case, and I don't know if you have noticed this or not, but you can try it. I'm pushing that deep freeze across the concrete floor, the concrete pad in my garage, and I have to apply a lot of force to get it to move. But once it's moving, I still have to require a certain amount of force, but it's usually not as much. And what that tells us is that forces of friction between objects are usually bigger if the objects aren't moving, but once they're moving, the force of friction is less. So the force of friction between two objects is greater if they're not moving, usually. There are very rare examples. Now, there are two types of frictional forces. One is called a static force of friction. This has nothing to do with static electricity. The word static here means unchanging. And in this context, it means that the object is stationary. So the stationary force of friction is the amount of force needed to get an object to start moving. Once the object is moving, there is still a frictional force that's less, and we call that the kinetic force of friction. Sometimes we refer to the kinetic force of friction as the dynamic force of friction. Now, I'm going to jump a little bit ahead here. We're not really going to need to know this for today's lesson, but it might help you understand what I'm talking about here. If I have an object that is on a surface, there's the object, it's sitting on a surface, and I apply a force to that object. And I apply a force of 2 newtons, and the object doesn't move. And then I apply a force of 3 newtons, and the object doesn't move. And I start pulling harder and harder and harder, and I get to 6 newtons, 6.1, 6.2, 6.3, 6.4, 6.5, and at 6.6 newtons, the thing starts moving. What that means is that if the applied force to get it to just start moving was 6.6 newtons, then that tells me that the force of friction is exactly 6.6 newtons. I do realize there's this little bit of acceleration to get it moving. But as soon as I apply that 6.6 newtons, it's going to be moving, and I can ease up a bit and basically have a situation where the acceleration is 0. What I am telling you is that the force needed to get the object to move is the static force of friction. So if it requires 6.6 newtons to initially start it to move, the static force of friction is 6.6 newtons. What you will discover most of the time, I'm just curious, I want to ask a question here, and you can give me a thumbs up if your camera's on, or you can type yes or no in the chat. And it's not a test, I just really want to know this. How many of you have experienced something where to get an object to move, it's quite difficult, but once it's moving, it's easier? Yes or no? Yeah, I think we all see that. You know, I don't have carpet in my house. And if I have a couch can be quite heavy, and when I go to push it to move it and slide it along the floor, I have to push really hard, but as soon as it starts moving, it almost gets away from me. So what's going to happen here is once it's moving, and I'm not going to redraw this, but once it's moving, in order to get it to continue to move at a constant speed, you might only have to apply 5.6 newtons. To have it move at a constant speed. It's still an acceleration of 0, but now it's going to be less of a force that you need to apply, and that means we're talking about a kinetic force of friction. But, you know, this idea, we're going to come back to it later on, is very important, that the applied force needed to have a constant velocity is the force of friction. All right. So forces of friction are related to the normal force acting on the object. In other words, when you go back and you look at that diagram that shows the normal force acting upwards, however big that normal force is, that plays a role in how much friction there is. So if the normal force is greater, there will be more friction. And I have a feeling many of you, if you think long and hard about this, you will be asking, well, why can't we just say that the force of friction depends on the gravitational force? This is very subtle. This is very conceptual this morning. Does the force of friction depend on the gravitational force? Yes, if the object's on a horizontal surface. But if it's on an incline, which we will deal with later today, we can get less friction by having a steeper incline. If I put a box on a horizontal surface and I tip that, if I can grab this, there we go, and I tip that ramp, I hope you would see that if I had a, let's say a big box of books on a ramp that was at an angle of about 20 degrees, it probably would not slide. Does that make sense to you that it would not slide? Yes or no? Okay? Yes, it would not slide. And that means that even though gravity is pulling the box towards the bottom of the ramp, there must be a force of friction in the opposite direction. I hope you would agree, though, that if we take that same box, that same situation, I don't know why my smartboard is kind of fried here. There we go. We take that same situation and I tilt it like this. I hope you would agree that the box would move in the second situation, yes? Okay. What that means, everybody, is that there is a force of friction here that's bigger than the force of friction here. The force of friction must be bigger if it doesn't slide in the first case. And even though it's the same box, it has the same force of gravity, the normal force will be less. And we're going to talk about that in the second lesson. So now let's get back to forces of friction. And a quick example. We have a 7.6 kilogram object resting on a horizontal surface. What's the normal force acting on the object? So we don't have a formula for a normal force, but what we can do is say that when you have an object on a horizontal surface, we know from the very first question that we looked at today that there is a force of gravity acting down that is exactly equal to the normal force acting up. And you certainly don't need to draw this every time. What you need to know is that for an object on a horizontal surface, the normal force is the same size as the gravitational force. And this is what I was talking about earlier. We do not have a direct way to calculate a normal force, so we calculate using the formula we learned yesterday, the magnitude of the gravitational force. I've got vectors in here, so I'm going to include a direction that's down. But we're going to take the mass, which was 7.6 kilograms, multiplied by 9.81 meters per second squared. And I'm just choosing to use the word down rather than writing negative. So we multiply those two numbers. And we get 74.6 newtons down. So the force due to gravity is 74.6 newtons down. Now, is that the same as the normal force? Is what I have just written, and I'm going to highlight, is this the answer to the question? Is this the normal force? The answer is no, it's not the normal force. The normal force will be 74.6 newtons up. Did you get that number, by the way, 74.6? Okay, good. So the answer to the question is 74.6 newtons up. And you might be sitting there watching this and going, oh man, he's making a really big deal out of something that doesn't need to be a big deal. No, it does. It's going to get complicated very quickly. So again, you don't have a direct way to find the normal force. There's no direct way to find it. What you do instead is you find the gravitational force, and then you look at this diagram. To reason out what the normal force would be. All right, now I have a question for you, and I'm going to give you a minute or two to think about this. There are, it turns out, only two things that determine the amount of frictional force between the surface. And I'm going to give you the first one. The first one is the normal force between the surfaces. Now there is another thing that determines the amount of frictional force. And I know that some of you might say the mass of the object. And I would say to you, yes, that is correct, but that is just a way to get a different normal force. If you change the mass of the object, you'll change the weight. And if you change the weight, the normal force will change. So there are lots of ways to change the normal force. You can talk about the mass being different. You can talk about the angle of the surface being different, which we are not going to talk about in this first lesson in detail. So there are some things that affect the normal force, but there is one other thing other than all of these and the normal force that determines the amount of frictional force. So I'm done talking. I want you to think about that for a second and think about what the second thing is that affects the normal force. So by typing yes or no, how many of you think you have an idea of what this other thing is that you could potentially put into words? So Liam is saying the composition of the objects. Andrea is saying the applied force. Now it turns out that, I want to address Andrea's answer first. Oh, and the area that it's touching. This is really good. This is really, really good. We have to talk about all three of these. Now, it turns out that Andrea is partly right. When you talk about applied force, though, Andrea, are you talking about pushing down on the object? Or are you talking about pushing the object horizontally? So any applied force externally is what you were thinking, but not gravity. Okay, so if there is some applied force that is in a downward direction, then what will happen is the normal force will grow. In other words, if I'm trying to push that freezer horizontally across the concrete pad in my garage, but you're just messing with me and standing to the side and you're pushing kind of at an angle towards the floor, that applied force will increase the force of friction, but only because it will increase the normal force. So it turns out that it doesn't have anything directly to do with the applied force. Now, Farhan said the area that is touching. So I have a feeling what Farhan is talking about is this situation, where you have, and we have to keep things constant. We have a surface, we have a box that has a particular mass, and I'm going to say that the mass is 100 kilograms. And then we have another box that has the same mass. It's made of the same material. And it's 100 kilograms. So am I right in understanding what you're talking about here, Farhan? That this box on the right has more surface contact with the surface? Okay. It turns out, everybody, this is in fact a very common misconception. It turns out that if these two materials are the same, sorry, I had to just turn my mic off for a second. It turns out that if these two boxes are made of the same stuff, and they are the same mass, and they are both on the same surface, the force of friction is the same. I think this misconception comes about because when you take a look at, for example, race cars have very, very wide tires. And I think there's probably even people involved in the racing industry who believe that the tires are wide to give you better traction. They do not give you better traction. The force of friction is the same. The difference is the wide tires spread out the force over a larger area, reducing the amount of wear and tear on the tires. But the force of friction is the same. And this is, I'm going to go off on a tangent here. This is the really crappy thing about learning this way. We have lots of lab activities, and I would demonstrate this to you right now because it's bound to come up, and I always have everything ready. I have a block of wood and an identical block of wood with the same mass but different sizes, and we measure the force of friction. And as long as their masses are the same, we get the same force of friction. What we do is we attach a spring scale . We attach a spring scale to this, and we pull it to the left until it starts moving, and we read the force, and that's the force of friction. We apply the same spring scale to this and pull it to the left until it starts moving, and when it does, we read the force on the spring scale. Whatever that force is, that's the force of friction, and we discover it's the same. It's really surprising, and I had that misconception as well. I thought, well, if it's a greater area, there's more friction. There isn't. It turns out that Liam has the best response here. It's the composition of the objects. It's the nature of the surfaces. And of course, now we're talking about changing something. We're changing the surfaces. So for example, if the surface that I'm trying to walk on is melting ice, there's very, very little friction. But if the surface that I'm trying to walk on is frozen ice at a very low temperature, there's still friction, but not as much. If I change the surface even further by sprinkling sand on that ice, then I've changed the nature of the surfaces, the composition of the objects. and there would be even more friction. I want to just add to what Liam said, though. It's not necessarily the composition of the objects. What he means is it's the composition of the parts of the objects that are touching each other. Right? We don't care about what the whole object is made of. We care about what the surfaces are made of. So for example, I just installed a bunch of stuff in my parents' home, and in the basement stairs, I installed on each stair this stuff that it's black in color, but it's a peel and stick kind of thing so that it creates more friction. It's a safety tread. So I haven't changed the stair. They're still walking on the stair, but the surface of the stair is different. So what we're going to put here for the second item is the nature of the surfaces. And looking at the clock, I feel as though I'm going maybe a little slow, so I better pick up the pace here. The nature of the surfaces. And what we call this is the coefficient of friction. And mathematically, it's a number. The coefficient of friction has a symbol that looks like that. This is a Greek letter called mu. Just like pi is a symbol in the Greek alphabet, mu is a symbol in the Greek alphabet. And if you have a coefficient of friction that's really, really tiny, you have very little friction. If you have a coefficient of friction that's quite large, you have more friction. And it turns out that if you multiply those two things together, the two things that determine the force of friction, if you take the coefficient of friction and multiply by the normal force, you get the force of friction. And this formula is on your formula sheet. Okay, let's use this formula now. Oh, actually, I got one more thing I want to show you. If you were to look up some coefficients of friction, so this table is from your textbook. Notice there's a coefficient of kinetic friction and there's a coefficient of static friction. Remember that static friction is a measure of how difficult it is to get an object to move, whereas kinetic is how difficult it is to keep it moving. And I told you that kinetic friction is usually less, and you can see that. So when you look at, for example, steel on steel, or steel on greased steel. So you take a piece of steel and another piece of steel and you put them together and you start rubbing them together, you have a coefficient of friction of 0.41. We'll talk about what that means in a second. But as soon as you put grease between the surfaces, you have this coefficient of friction. A rubber tire on dry concrete, the coefficient of friction is quite high. It's 1. And again, we'll talk about what that means. Rubber tire on ice, this is why in the winter when the roads are very icy and you know you're going to be turning someplace, you ease off on the gas and let the engine compression slow the vehicle down before you hit the brakes. Curling stone on ice, very, very little friction. Teflon on Teflon, very, very low. I don't know what synovial fluid is. I think that might be a medical thing. You could certainly look it up, but it's very, very small. Waxed hickory skis on wet snow, again, kind of sticky. I don't know if you've noticed this, but wet snow is sticky. But loose snow or dry snow is more slippery. All right, now we're going to take a look at some examples. A 7.6 kilogram object is pulled along a horizontal surface. The kinetic coefficient of friction is 0.2. What is the force of friction? Well, we go to the formula. And by the way, this formula for force of friction, we never worry about direction in it, ever. It's the coefficient of friction times the normal force. Okay, well, the coefficient of friction is 0.20. What is the normal force? Give you a minute to think about that. What is the normal force, or how can we find the normal force? Anybody want to take a stab at that? Excellent. Find FG. The reason we're going to find FG is it's a horizontal surface, and the free body diagram for a horizontal surface says that the force of gravity acting down is exactly equal in magnitude to the normal force acting up. So we're not going to actually calculate the force of gravity just yet. I want to add something to what we've just said. This is the normal force. This is the force of gravity. And the normal force has a magnitude that's equal to the magnitude of the force due to gravity. So my question to you, I guess, is, does this, in particular, this conclusion, make sense to you? Can I get some people to type yes or no? Okay, so how often are we going to have to draw that? Are we going to draw that every time we have a question with an object on a horizontal surface? No. What we are going to do is take this formula. In fact, I'm going to erase the point too. We're going to take this formula and write this. I don't want you saying to yourself, oh, I have to calculate the force of gravity. What we have done is we have said that this is equal to the magnitude of the force of gravity, but the magnitude of the force of gravity is just the mass times the magnitude of the gravitational field strength. And, you know, if I want to be very clinical about this, I guess I should write this. I'll tell you right now, what I will often write is FF equals mu mg without the vector symbols. And I hope everybody understands that these two are the same. It's just that the bottom one is cleaner. Now, before we finish this question, some of you are going to memorize that bottom formula, and that bottom formula only works if it's on a horizontal surface. Okay? It's okay to use that if it's on a horizontal surface. So we put the numbers in. You're going to have the force of friction equals 0.2 times the mass times 9.81 meters per second squared, and we calculate that. And you get 14.19 newtons. So I'm going to say 15 newtons. The force of friction has a magnitude of 15 newtons. And now I just want to briefly explain to you what the coefficient of friction is really measuring. And again, we would do a lab, and I think when we get back to school, we will do a lab with this. We're going to end up probably doing a whole week of labs because we will have time, because we're not going to spend a bunch of time reviewing for exams. If I rearrange this equation, I get mu equals the force of friction over the normal force. And really, that's the way to look at it. If mu, for example, is 1.0, what that means is the force of friction will be 100% of the normal force. If mu is 0.2, like it was in our example, what that tells you is the force of friction is only 20% of the normal force. So it's a ratio of the force of friction to the normal force. Let's take a look at number 2. sorry, number 3, a 25 kilogram block is initially at rest on a horizontal surface. Okay, so I'm not going to do this every time. It's on a horizontal surface. Is this a true statement? Is this a true statement? I tricked you, it is, because I don't have vector symbols. you got to be careful here. If I put vector symbols up top, then it's false. This is simply saying the magnitudes are equal. What that means in this question is that the force of friction equals mu times m times g. This is what we can use because it's horizontal. Now, if a horizontal force of 75 newtons is required to get the block to move, then 75 newtons is the magnitude of the static force of friction. We talked about that earlier. The force required to just get an object to move is the static force of friction. If after we're done getting it to move, it requires only 60 newtons, then this is what's referred to as the kinetic force of friction. So we want to determine the coefficient of static friction for both of these. It's not a difficult problem once we've set it up. For mu static, we are going to have the force of friction is 75 newtons equals mu times the mass times 9.81. For the coefficient of kinetic friction, we are going to have the exact same thing, except it will be 60 newtons. So I would like everybody to calculate those two quantities and give me some answers. Type out some answers for me so I can check to see that you're getting it right. Don't forget, you either have to put the mass times 9.81 in brackets before you divide, or calculate what it is and then divide by that result. Again, I am asking you to 0.31. So Liam's got 0.31 for the static and 0.24 for the kinetic. So does Farhan. And in fact, that is what you get for these. Evan got that. Andrea got that. I got that, so it's safe to say, since we're all in agreement, I know that physics is not a democracy, but I can't see us making any mistakes here. Daniela, Cole, Tyson, Isaac, you're all getting the same thing, 0.31 and 0.24. So before we move on here, any questions with that example? What I am basically going to be doing, everybody, for any questions where we have a horizontal surface, is I'm immediately going to be saying the magnitude of the force of friction is mu mg. This is going to get more complicated later, but if it's a horizontal surface, we can do that. The coefficient of static friction between a 10 kilogram object and the floor is 0.5. What's the maximum horizontal force that can be applied before it starts moving? Well, that's going to be the force of friction. So all we're going to do is we're going to calculate 0.50 times the mass of 10 kilograms times 9.81 meters per second squared. Just being in teaching mode here, I don't care about the units. I want to say 49.05. So this works out to 49 newtons. The lengthy part of this unit, or this lesson, is me explaining to you why we can use FF equals mu mg without regard to direction. But in the next lesson, it's not going to be that simple. Number 4, a 5 kilogram block is moving with an initial speed. It encounters a rough surface where there's a coefficient of friction. So what happens is maybe the block is on ice and then it hits something rough. While the block is moving, when it hits that rough surface, the block is moving with a certain speed, 22 meters per second to the left. So this is not a force that I'm drawing, it is a velocity. At some later point in time, its velocity will be 0 meters per second. Why? Because while it's moving, and this that I am drawing now is a force, while it's moving, there is a force of friction backwards. And that force of friction, well, I'll ask you another true-false statement. Is this true? Oh yeah, this is the second number 4, right? Okay. This is a true statement, you guys. The reason it's true is net force means total force acting on the object. And if you look at all of the forces acting on this object, remember this 22 meters per second is not a force. There is also a gravitational force down and a normal force up, but these two forces cancel. So all of a sudden this got really tricky. We have a gravitational force acting on it. We have a normal force acting on it. There are 3 forces acting on this object while it is skidding to a stop. And the word net means we add those forces together. But when we add those forces together, the gravitational and normal forces cancel. So the bottom line is that the force of friction is the net force, which means if we can find the force of friction, we can set it equal to ma. We can do the following. ma, which is how we calculate the net force, and I don't care about direction, equals mu mg, which is how we calculate the gravitational force. This is tricky. All of a sudden, this became tricky. And it's going to get trickier later. Why am I worried about finding acceleration? Because if vi is 22 and vf is 0, and we want to find the displacement of the block, we need to know the acceleration to do a kinematics calculation. So we can go ahead and put all of the numbers in here. 5 kilograms times the acceleration equals mu 1.15 times the mass, which is 5, times 9.81. So I would like everybody to find the acceleration for me, please. Curious, did anybody, if you look up here, did anybody notice that we could cancel the masses? Which means the mass doesn't matter in this particular question. The acceleration can be found by taking mu times 9.81. That is going to be important for later as well. So let's see. I chose to cancel the masses. Do you get 11.2815 meters per second? Okay, squared. So 11.2815 meters per second squared. Now, I hate to keep doing this to you, but I'm going to ask you a true-false statement. Is the acceleration of the object, what was it? Equal to 11.2815 meters per second squared. Is this a true statement? And the answer is no, it's negative. Because the acceleration is in the opposite direction of the motion. If you were to use a positive acceleration, you would get a negative displacement, which doesn't make sense because it's moving, in this case, to the right. So now we have to use A, VI, VF to find D. I think the cleanest approach is to use this. So VF squared is 0. VI squared was 22. Plus 2 times negative 11.2815 meters per second squared times D is 22 squared 484. So you get 484 minus 22.563 is 2 times 11.2815, 22.563. Okay. D, okay, it's a grade 8 equation to solve. In high school, of course, I would move that 22.563D to the other side where it becomes positive. So if we take 484 divided by that 22.563, we're going to get the answer. It's going to be somewhere in the neighborhood of 20 newtons. I said it's going to be somewhere in the neighborhood of 20 newtons, and I misspoke. It's going to be somewhere in the neighborhood of 20 meters. This is a displacement, so it's meters. So I'm going to say it's 21 meters. And now, before I explain the rest of the day to you, questions. First of all, questions with this example. I guess before you do, I'll review. This free body diagram that you're looking at does not include the 22 meters per second. That is not a force. The three forces acting on the object are given and they're highlighted. when I add them together, I'm going to back up. The reason I'm adding them together is I need acceleration to answer the question. And acceleration is related to net force. And net force is going to be found by adding those forces together. So I need to look at this diagram. Let me approach that in another way. For you to determine acceleration, for you to determine the acceleration, you are going to need to know the net force, because net force equals ma. The way to find the net force is to look at the free body diagram and add the forces together to get the net force. Does anybody have any questions with that example? Example, the second, number 4. Okay, another thing I want to review here. I know that many of you are going to get in the habit of simply using force of friction equals mu mg. And whenever you use that, if you get a wrong answer, the first question I'm going to ask you is that a formula on your formula sheet? And the answer is no. That's not on your formula sheet. What's on your formula sheet is the force of friction equals mu times the normal force. So how do we get from here to here? On a horizontal surface. The magnitude of the normal force and the magnitude of the force of gravity are the same. I didn't put vector symbols there, so that's a true statement. So what we end up doing is we replace Fn with Fg, and then we use the fact that Fg has a magnitude of m times g. So, I guess I just really want to highlight for you the fact that you can only do that if it's a horizontal surface. Okay, now I have a question for you. Same thing I've been asking frequently. Too fast, too slow, just right in terms of the content, in terms of you sitting there understanding this. Okay, I think I got enough feedback. I'm going to do the same thing that I did yesterday. I really believe, everybody, I hope you see, had we done this yesterday after the first lesson, we wouldn't have even had enough time. And you'll have to trust me that I think if I move on and start talking about inclined planes today, even though the lesson may look short, it's complicated. And you have lots of problems here dealing with this lesson. So I am not moving on to the next lesson today. But what I am going to say is that I want you working on this until 11:45, and at 11:45, I'm going to be going over homework questions. I may be going over stuff in between as well. But from about 11:45 to 11 o'clock, I'm going over problems with you, okay? We have lots of time. Don't worry about time. I've readjusted my calendar, and by removing review days for exams, which we're not having right now, we've got boatloads of time, okay? So get to work, please, on those problems, and if you have questions, let me know.